Hello and welcome to Elucidations, a philosophy podcast recorded at the University of Chicago. I'm Matt Teichman.
And I'm Jamie Edwards.
With us today is Patricia Blanchette, professor of philosophy at the University of Notre Dame, and she is here to speak with us about the Logicism of Gottlob Frege. Patricia Blanchette, welcome.
Thanks very much, Matt. Jamie?
So Logicism is usually described as the sort of research program in philosophy from the end of the 19th, beginning of the 20th century, whose basic idea was that mathematics could be reduced to logic. What does that mean exactly? What would it be to explain mathematics in terms of logic or reduce mathematics to logic?
Well, it turns out there are a number of different things people have meant by that. What Frege meant by it was pretty straightforward. He thought that most of mathematics, which includes arithmetic, that is the theory of your ordinary numbers, 1, 2, 3, 4, 5, plus the rest of the integers, the negative numbers, plus the rational numbers and the real numbers, all of those, but not including geometry. Okay, so what I'll use the term arithmetic for covers all the stuff having to do with all the numbers. So Frege thought that the truths of arithmetic, things like 2 plus 2 equals 4, every prime number there's an x prime number after it, and things like that. All of those facts about the numbers could be proven using just principles of logic. So the reduction for him was a matter of proof. You can prove every arithmetical truth just using logical principles.
So the claim is that all mathematical truths are logical. This is not a claim about how mathematical truths are discovered or applied. Is that correct?
That's right. Frege really didn't take himself to have a psychological thesis. He didn't take himself to have a thesis about how children actually learn the arithmetic that they learn. But he did take his logicist claim to be important for understanding something about the foundations of our overall knowledge of arithmetic. So there's a sense in which he thought that because arithmetic really is just complicated logic, you can explain how people know arithmetic just by explaining how they're in a position to know principles of logic. And that for him meant that because you can know principles of logic just by pure reasoning, just by thinking hard, and thinking about things like this. Well, if some claim is true, then the denial of that claim is false. That's a principle of logic. Or if you have a claim, call it P, and a claim Q, if the claim P and Q is true, then P is true. To know that, all you have to do is think about what and means and reason a little bit. So that's what he meant by logical knowledge, that kind of pure reasoning. So for him, the claim that arithmetic is reducible to logic implied that people can, in principle, come to know truths of arithmetic just by doing that kind of reasoning in a somewhat complicated way.
So the motivation for the program of Logicism then is something like giving an account of the nature of mathematical truths. Is that the motivation?
Yes, absolutely. Frege thought that he was going to give an account of the nature of mathematical truth and of the nature, therefore, of mathematical knowledge. Yes. So in particular, he disagreed with people who thought, for example, that mathematical truths are about collections of objects in the world in such a way that you would learn the truths of mathematics by manipulating pebbles or something like that. This was a view that he attributed, maybe accurately, maybe not, to John Stuart Mill. Mill, who was an empiricist, as you know, so an empiricist is someone who thinks that all of our knowledge comes through our senses. And so how do you learn truths of mathematics? Well, you look at 2 pebbles and you look at 3 pebbles and you push them together in a pile and you count 5 pebbles. You do that a few times and then you come to know that 2 plus 3 equals 5. This is a theory that it's not as absurd as I've just made it sound, and there may be something to it, but it's a theory that's very difficult to use in order to explain how we know things about very large numbers, or how we know things about irrational numbers, or how we know things about infinite collections of numbers. So 2 plus 3 equals 5 is kind of easy, but most of mathematical knowledge is kind of hard to explain in terms of our empirical access to things like piles of pebbles, or anything that, in fact, that we can know about through our senses. Frege thought that was the wrong way to go. He also thought that various other accounts were wrong about the nature of mathematical knowledge. He thought that once you understand that mathematics really is just complicated logic, you will then know that we don't need our senses to come to learn the truths of mathematics, and we don't need anything else other than our ability to reason in purely logical ways. So that was the idea.
Okay, so it's very intuitive that if the sentence P and Q is true, then the sentence P has to be true. So P just follows from P and Q.
That's right.
You know, if I'm wearing a black hat and a red shirt, then it follows from that I'm wearing a black hat. But intuitively, this seems pretty different from the claim 2 + 2 = 4. So how exactly do you get from these basic sorts of examples that we've just been discussing of drawing logical inferences to numbers? How do you translate these statements like 2 + 2 = 4 into statements like Matt has a black hat and Matt has a red shirt, therefore Matt has a black hat?
That is a really good question. And the answer is a little bit long and complicated if we go into the details, but I can sketch the basic picture, I think. So what Frege thought was that you can take a sentence like 2 + 2 = 4 and spell out what it means. And I'll come back to what he thought it means in a minute. Spell out what it means in a way that makes it turn out to be somewhat more complicated in structure than 2 + 2 = 4. Then once you've done that, you can give a proof of that, as it were, fully fleshed out, fully analyzed version of 2 + 2 = 4. And that proof that you give is going to have as its premises only principles of pure logic. So now that may sound like magic, right? That somehow you would use principles like the one that you just gave us about your black hat and your red shirt and get from that to 2 + 2 = 4. So let me say a little bit about how the transition goes. So first, let's start with Frege's view about what numbers are for. He thinks that the ordinary numbers, 1, 2, 3, 4, 5, are used primarily for counting things. So I'll say there are 3 people sitting at this table. So that's the primary, basic, most important use of the number 3, is that the number 3 is something that you talk about when you're counting things. I tell you what, let's start with what it would mean to say there are 0 people at this table, because 0 is a really nice number as far as Frege is concerned. To say that there are 0 people at this table is just to say there's nobody at the table. What is it to say there's 1 person at the table? Is to say, well, there's something, call it X, at the table, and for everything in the world, if it's at the table, then it's X. And that's a way of saying, it's convoluted, but it's a way of saying there's exactly 1 thing at the table that doesn't mention the word 1. Okay, how about 2? We'll go as far as 2. What does it mean to say there are 2 people at the table? It means, well, there's an X at the table, and there's a Y at the table. And for anything, if it's at the table, then it's either our favorite X or our Y. So that means there aren't any other things. So that was a very, very, very long-winded way of saying there are exactly 2 things at the table. So you can go on like this, of course, and say there are exactly 3 things at the table, or there are exactly 4 things at the table, without mentioning the words 3 and 4. Okay, so there's the beginning of our reduction. Now, for Frege, what you do is you analyze what the numbers are by analyzing those kinds of statements about numbers. And the kinds of statements he was interested in were things like there are 0 such and suches, there's 1 such and such, there are 2 such and suches. And at the bottom of this was also an account of claims like this: there are just as many such and suches as there are so and so's. So there are just as many people at this table as there are chairs at this table. And for Frege, what that meant is you could match up the people and the chairs so that every person gets a chair, every chair gets a person, nothing's left out, and you don't have 2 people in 1 chair or 1 person on 2 chairs. You just match them up, as we say, 1 to 1. And that notion of matching up 1 to 1 turned out to be very, very, very important for him when he was assessing statements that have to do with numbers. So you say, to say there are just as many of these as there are of those is to say you can match the these up with the those 1 to 1, and that means the number of these is identical to, right, is the same thing as the number of those. So he thought that statements about numbers that say this number is equal to that number were very, very, very important, and that you could explain the meaning of those by in terms of the matching up 1 to 1 of the things on the one hand with the other things on the other hand, like the chairs at the table and the people at the table. So that gives you a rough idea of some of what goes on here. He takes talk about 3 and 4 and 5 and talk about prime numbers then and things like that, and explains them in terms of talk that doesn't mention those numbers themselves, but which in some sense he thinks means the same thing.
Yeah, so it's a pretty clever trick, actually, when you think about it. If you want to define what a number is, you don't want to just have the word number in your definition of number. That seems kind of circular and pointless. You don't want to say there are just as many people as there are chairs. Just means, well, if there are 3 people and there are 3 chairs, then the 2 numbers are the same. You want to find a way of defining number without using the word number in your definition. And the way you do that is you say that there's a correspondence. So correspondence isn't the same as a number. It just means that, look, for each thing in the one group, I can draw a line from it to something in the other group. So that's the trick that allows us to understand what numbers are in terms of something else, namely matching pairs of things together.
Yeah.
One of the interesting things about, as it were, translating mathematical statements into logical statements is that, in principle, it gives you a new way to check whether the mathematical statement you're thinking about is true. I mean, so obviously everybody knows that 2 + 2 = 4 is true, but maybe a more complicated one, like a really complicated equation or something. It's not totally obvious whether it's true or false. And maybe this method of translating mathematical statements into logical statements can give us a different way to check to see if the mathematical claim we're evaluating is true or false. Was this sort of the idea behind the Logicism program, that you could come up with this sort of automatic way of checking whether mathematical proofs were correct?
No, but that's a great question, because when you look at the work of a logicist, someone like Frege or some later logicists, what you see are a bunch of proofs. And they're very, very, very careful proofs. They're much, much, much more careful than anything that gets published in a mathematics journal. And I can return to the reason for that in just a moment. But this might lead you to believe that what they're trying to do is give proofs that are better in the sense of somehow more error-free than the proofs that a mathematician might give. And so you might get the impression that the logicists were trying to make sure that mathematicians aren't really making mistakes. But that, in fact, isn't true. So Frege, in particular, had no doubts about mathematicians' ability to prove things. And he had no doubts about the truth of the kinds of things that he was, in fact, setting out to prove. Things like, as you say, 2 + 2 = 4. His reason for giving proofs, and for giving stunningly rigorous proofs, was so that he could be very sure exactly what principles were needed in order to prove the conclusions. So the proofs then were laid out in a very rigorous step-by-step fashion, not so as to ensure that the conclusions were true, nobody doubted the conclusions, but so as to make it really obvious what principles you needed to use in order to prove them, so that we could see what, in fact, they, as Frege puts it metaphorically, what the truths rest on, what their grounds are, or what it is that guarantees that they're true. So his proofs were, as I say, sort of stunningly rigorous. And one of the things that was really neat about his way of proving things was, in order to bring a sense of rigor to the proofs, he invented a new system for doing logic. He invented a new way of writing down proofs such that the steps were much, much, much more rigorous than anything that had been seen before. And even the very formulas that he used to express things, like the fundamental principles of logic or the more complicated sentences of arithmetic, more complicated truths of arithmetic, the sentences that he used, the formulas that he used to express them, were much better at showing the kind of structure of the truths in question. And so what you end up with in Frege is the first system of what we now think of as formal logic. So instead of using a natural language like English or German, would have been his language, instead of using German to write the proofs, he wanted to make sure that he was as explicit and rigorous as possible, so he moved to what we call a formal language, which is really, really rigorous. And you have to learn it in order to do the proofs. It's not hard to learn. It's not like learning a natural language. It only has a few kinds of words in it. But it's a language that's really, really good for doing logic in. And it's a language that evolved into the languages that we now use for doing logic. So though Frege's main goal wasn't to come up with a system of formal logic, he was doing that just as a sidelight, just as a means of doing what he wanted to do, which was to prove the truth of Logicism. On the way, he did this most amazing thing. He came up with what we call quantified logic, a formal system of quantified logic, which is very, very similar to what we use today.
So if Frege's Logicism were to succeed, he would solve a big problem, which is understanding the nature of mathematics, because he would be understanding it reducing it to logic, and thereby understanding it in logical terms. Does he think that logic now, understanding the nature of logic, is easier to handle, or is that itself going to be a major task?
Oh, nice question. That itself is, in some sense, a big task. It's not one that he took himself to have very much to say about. So you might wonder why it is that showing that mathematical knowledge really is just a species of logical knowledge, why does that help? After all, it might be kind of hard to understand what logical knowledge is all about. That's a very good question. And one thing you might say, at the very least, is that it would reduce two hard questions to one hard question, which perhaps is progress. But in fact, it may be a bit better than that, and I think Frege thought it would have been a bit better than that. So let me back up and say why mathematical knowledge is so interesting and hard to explain. So when we think about the different kinds of knowledge that people have, it looks like we can split them up into two camps. One camp is the kind of knowledge that you need to use your senses to figure out. So mundane things like the sun is shining today, but even more general things like the basic principles of chemistry and geology. We know those by experiment. We use our senses. We have what we philosophers call empirical data. So those parts of our human knowledge have to be explained by looking at the way in which we get information in through the senses. And then we combine that and we get general truths about the world, and indeed truths about the world that we sense. Okay, so that's how chemistry, geology, physics, astronomy, all of those sciences work. Mathematics looks very different. If you go to the mathematics department, you don't find any microscopes, you don't find any telescopes, you just don't find anything that makes it look like mathematicians have to use their senses very much. What mathematicians do, it seems, is they just sit around and think, and they can do it in the dark if they want. They just don't need really anything that comes in through the senses. But here's the cool thing about mathematics. You don't need information about the empirical, that is sensory. You don't need anything about the empirical world in order to come to know the truths of mathematics, but you need mathematics in order to do anything in the empirical world. You cannot build a bridge without knowing your calculus. It'll fall down, right? So that's a really amazingly cool thing, I think, about mathematical knowledge. It looks like it comes in a non-empirical way, but in order to do anything out there in the world with the empirical world, you need mathematics. And so the question is, how can mathematics be so useful about the world of our sensation, but not be grounded in the world of our sensation? And let me just put this in a contrast. Suppose you wanted to do a chemistry experiment. Well, you'd have to know how the chemicals are going to interact. But in order to figure that out, you've had to have experience of chemicals. And so it makes sense that the chemical knowledge you have comes from experience and it's useful for experience. But math looks weirdly different. It doesn't seem to come from experience, but it is useful for experience. And so this puts us in a position, one might think, of thinking of mathematics as uniquely interesting to explain. That is to say, our mathematical knowledge looks particularly uniquely interesting to explain. So now, the thing that would come out of reducing mathematics to logic might be this. You might discover that, oh, I see why mathematics is so useful. Logic is pretty darn useful, right? If I want to know that it's Tuesday, perhaps all I need to know is there are only 7 days in the week, and it's not Monday, and it's not Wednesday, and it's not Thursday, and it's not Friday, and it's not Saturday. Did I cover them all? I don't know. It'll follow from that it's Tuesday. That is to say, I can use logic to figure things out, and I can use logic to figure things out about the empirical world sometimes. If I know that all snails have this particular physical feature, and that's a snail, I can deduce, without even looking at it, that snail has this particular physical feature. So logic, it looks like, actually has the characteristic that we're interested in. Logic is useful in the empirical world. We use it all the time. You can't do anything without using logic. But in order to know the truths of logic, you don't have to have any empirical data. And so it might be that is still mysterious, and indeed I think in some sense it is, but it doesn't look mysterious that I can reason from all snails have this feature, and Snuffly is a snail, to Snuffly has this feature. There's nothing magical about that. It's just what I mean by these words. So the fact that logic has these characteristics, that is to say, logical knowledge is not empirical, but it's very applied, very useful, means if I can show you that mathematical knowledge is just a species of logical knowledge, I will have solved a large part of the really interesting problem of how mathematical knowledge can be like that. So that's, I think, one of the reasons that Logicism is a really attractive, interesting thesis, and it would have been nice if it had turned out to be true.
So we just said that it would have been nice if Logicism had turned out to be true. That suggests that there was some sort of deep problem with Logicism. And indeed, the philosopher Bertrand Russell discovered that Frege's logicist theory led to a certain paradox. And this led to what you might call a collapse in at least the original version of Logicism, a collapse in the whole enterprise. So what happened there?
Well, great question. Although, let me correct one small thing. What Russell revealed to Frege was not that Russell's logicist thesis, namely the thesis that arithmetic is reducible to logic. He didn't reveal that that leads to a contradiction or a paradox. What he revealed was slightly different, that Frege's way of trying to prove logicism was problematic. And so let me say something about what the problem was. So first of all, just as background, it's probably worth knowing that Logicism really was a huge project for Frege. It was really, I think, the focus of his life's work, though he did a lot of other interesting things, which maybe we'll get a chance to talk about. Really, Logicism was what he was trying to do throughout most of his life. He was trying to demonstrate in an unbelievably rigorous way that the truths of arithmetic are truths of logic. He did this in a series of books. The first one, not really a book, just sort of a monograph in 1879, then something else in 1884 that pushed the project a little bit further, and then another book that came out in 2 volumes, the first volume in 1893, and the second volume was, well, it came out in 1903. It was actually at the printer, apparently, in 1902, when Frege got a letter from Russell. Now, let me say something about this book that was at the printer in 1902. It was supposed to be the second of probably 3 volumes that were absolutely conclusively demonstrating the truth of Logicism by giving these unbelievably rigorous proofs. These are proofs that it's really hard to even work through them, let alone to come up with them. They were the fruit of years and years of dedicated hard labor on Frege's part. And again, the labor was a matter of taking a bunch of very, very primitive, what looked like really basic, obviously true axioms of logic, and using them to go step by step by step by careful step, and getting at the end a truth of arithmetic. And so that was the project. Anyway, in 1902, in the summer, Frege got a letter from Bertrand Russell, who had been working through Frege's book. And Russell said, I think there's a problem here. I think that given what you think of as an axiom of logic, and so something that should only lead to truths, I think you can prove a contradiction. That is, you can prove something false. And Russell was absolutely right. There was a fundamental problem at the very heart of Frege's logical system. The one axiom is called axiom 5, and it's an axiom that tells you about certain kinds of objects, which Frege called value ranges, but they're very, very similar to what we today call sets. So I will talk about them as if they're really sets, though there are some problems with doing that. In any case, we'll call them sets. So this principle was really important to Frege's system because the numbers on Frege's way of analyzing arithmetic were supposed to be sets. And so when Frege's principle that basically tells you what kinds of sets there are and what the basic truths about them are, when that principle turned out to be false, that meant that the whole way of proving truths about arithmetic turned out to not work. That is, again, one of the principles that Frege thought was logical turned out not to be logical because it led to falsehoods. And it was a principle that was really, really, really important. And it turns out that, at least as Frege understood it, there really was no way to resuscitate the program. You couldn't just make a little fix here or there. Frege thought that Russell's paradox, which is the paradox that you can deduce using Frege's system, Frege thought that Russell's paradox showed that his whole approach to the analysis of arithmetic and the proof of arithmetical truths was just bad. It was just problematic from the beginning. Now, there are some people these days in the 21st century who think that Frege was a bit hasty in dismissing the logicist project in light of Russell's paradox. And so there's a new movement that's called neo-logicism, and we can come back to that in a minute. But maybe I'll pause here and say something about what Russell's paradox was, because it's actually fairly straightforward. Maybe not simple, but straightforward. So here's Russell's paradox. You might think that given any property, like the property of being red or the property of being a basketball, there's a set of things that has that property. The property of being red, well, so there's a set of red things. The property of being a basketball, well, so there's a set of all the basketballs. So that's the basic idea. For any property, there's a set of the things that have that property. Now, think about some weirder properties. Think about the property of being a set. So there should be a set of all the things that have that property. That is the set of all sets. How about the property of not being a basketball? Okay, it's a big set, so there's a set of all the things that aren't basketballs. So some sets are kind of weirder than others. Now, here's a property that some sets have and some sets don't have. It's the property of being a member of itself. So think about that for a moment. What kinds of sets would have the property of being a member of themselves? Well, the set of all sets, that's a member of itself because it's a set, right? The set of all non-basketballs, okay, it's not a basketball, so it's a member of itself. The set of all tables, it's not a table, so it's not a member of itself, okay? So think about the world of sets as divided into two. There's the bunch of them that are members of themselves. There's the bunch of them, really the more normal ones, that are not members of themselves. Okay, so now we have this property, being a member of yourself. Now, let's think about the set of things that have that property. Okay, so it's the set of all those sets that are members of themselves. Okay, so the set of all sets is in there, the set of all non-basketballs is in there, etc. Okay, now just one more complication. Think about a slightly different property. This is the property of not being a member of yourself. Okay, so which sets have that? The set of all tables, the set of all red things, stuff like that, right? Those sets are not members of themselves. Okay, so the property of not being a member of itself. Think of, now, we're getting to the end here, think of the set of things having that property. The set of all things that are not members of themselves. Got it? Okay, it's the set of all things not members of themselves. Now ask yourself this question. Is that set a member of itself? And it turns out that you're not going to get a good answer here. So let's think through why you're not going to get a good answer here. So the set of, let's call it R. R for Russell. R is the set of all those sets that are not members of themselves. And ask yourself this, is R a member of R? Ooh, well, if R is a member of R, then it must have that property that all of its members have, namely not being members of themselves. Oops. That means if R is a member of R, then R is not a member of R. That won't work. Okay, so R is not a member of R. Good. But you can't take a deep breath yet, because if R is not a member of R, then it has that property that all and only the members of R have. So it is a member of itself. So from the supposition that it is a member of itself, we reached the conclusion that it isn't a member of itself. And from the supposition that it isn't a member of itself, we reached the conclusion that it is a member of itself. So there is no way this set can exist. It can't be a member of itself, and it can't fail to be a member of itself. The reason this is called Russell's paradox is that that basic principle that for every property there is a set of things having that property, that principle is what we just used to reach what philosophers like to call a contradiction. The contradiction is a claim of the form some claim and its negation, right? And that can't possibly be true. So the contradiction we reach here is that R is a member of R and R is not a member of R. That's the contradiction. So the fundamental principle led to a contradiction, so the fundamental principle is false. And that principle was, for every property, there's a set of things having that property. Frege thought that fundamental principle was true, and that was really, really important to the whole way he analyzed arithmetic. And so now that that fundamental principle turns out to be false, Frege thinks there's no logical principle from which you can prove the existence of anything like sets. And you needed to do that to do logicism the way Frege wanted to.
So Frege took this paradox to be devastating to his own account of logicism, but Russell did not. Russell was working on a logicist program as well. So why did Russell not find this to be devastating of logicism in general?
Good, good. Well, for Frege, the idea was, again, to reduce arithmetic to the kinds of obvious principles of logic that we were talking about at the beginning of this podcast. Things like, if I have a black hat and a red shirt, then I have a red shirt. Things that were so obvious that you couldn't question how we know them. We know them just through very, very simple reasoning capacities. Okay, so Frege wanted the principles at the very basis of his system to be that obvious. And in order to call them principles of logic, they had to be that obvious. That was his idea. When Russell's paradox comes along, we realize, Frege realizes, and Russell realizes, that the principles that Frege thought would work won't work. Frege thought, and there aren't any other principles that are sufficiently obvious that will work for generating arithmetic. Russell thought, well, it's still a really interesting question to see what kinds of basic fundamental principles we can use to generate arithmetic. So what Russell does is he replaces the problematic principle that Frege had with a few more principles, which turn out to be not problematic. That is, they don't lead to paradox. And from them, you can do something like what Frege was trying to do. That is to say, you can deduce a bunch of, not all of, interestingly, but you can deduce a bunch of mathematics from the fundamental principles that Russell took as the basis of his system. The big difference here is that those fundamental principles that Russell takes as a basis are principles that don't have any obvious justification. They're not obvious in and of themselves. Russell took them to be very, very interesting principles, and they are very interesting principles for lots of reasons. But what justifies them, basically, is the fact that they are enough to give you mathematics. They're not as obvious and self-evident as Frege wanted his principles of logic to be.
So Russell unearthed this difficulty in Frege's original version of the Logicism program, and it turned out that there were some problems with Russell's solution to his own difficulty that he raised with Logicism as well. Where does that leave us today? Is the Logicism program mostly of historical interest? Does it have something to teach us about the nature of mathematics, nature of logic, nature of human reasoning, or justification?
Well, let me start by saying a couple things about why people don't follow Russell's Logicism, why Russell's project that he pursued actually with Alfred North Whitehead in a 3-volume work called Principia Mathematica that was published from 1910 to 1913. Why people don't think that that established the truth of Logicism. And here there are two big issues. One issue is that, as we were just talking about, the fundamental principles, or as we call them, the axioms, that Russell and Whitehead use at the basis of their system don't strike most people as principles of logic. They are, again, useful, interesting axioms, but they're not purely logical. Then a much more probably historically earth-shattering thing happened, which is that Kurt Gödel proved what's called now the incompleteness of arithmetic. And the incompleteness of arithmetic shows us, in a nutshell, that there isn't any way to take a manageable collection of axioms, of the kind that Frege wanted, of the kind that Russell wanted, and use them in such a way that you would be able to prove from them every truth of arithmetic. It turns out, interestingly, and really very surprisingly, the truths of arithmetic are an incredibly unmanageable collection of truths, which is to say, there is no set of axioms from which all of the truths of arithmetic are provable, which is a really cool, exciting, and really, I think, rather stunning thing to discover about arithmetic. Now, what does that have to say about Logicism? Logicism, the thesis that the truths of arithmetic are truths of logic, doesn't actually require that the truths of arithmetic are provable from a manageable collection of axioms. After all, it just requires that the truths of arithmetic are truths of logic, and maybe the truths of logic aren't provable from a manageable collection of axioms. Nevertheless, the way that Frege was trying to prove Logicism, and the way that Russell and Whitehead were trying to prove Logicism, was to take a manageable collection of logical axioms and prove from them a manageable collection of truths from which they thought all the truths of arithmetic could be proven. And that's the step that turns out to be wrong. There isn't a manageable collection of arithmetical truths from which the rest of the truths of arithmetic can, in principle, be proven. So what the incompleteness theorem does is it shows us not that Logicism is false necessarily, but that the straightforward way of trying to demonstrate the truth of Logicism will not work. So that is something that, in fact, Frege never knew about. He died in 1925, and this result comes about in 1931. So we don't know what Frege would have said about it, but he would have found it, I think, somewhat surprising as well. And indeed, I think Russell and Whitehead did as well. So that's one reason that you can't pursue logicism today in quite the way that either of our players here, Frege or Russell and Whitehead, were trying to pursue it. It also means that if you think of the truths of logic as what you can prove from some manageable collection of axioms, then in fact logicism is false. So in light of the incompleteness theorem, you can only be a logicist if you think that the truths of logic are an interestingly unmanageable collection of truths. So now there's the other question you asked, which is sort of what's the status of logicism today? So there are some people who think for those kinds of reasons that logicism really ought to be abandoned, that it's no good. And that may be because they think of the truths of logic as pretty manageable. And so the truths of arithmetic are just not going to be reducible to the truths of logic. On the other hand, there is a research project ongoing now, which has earned the name Neo-Logicism, which is a research project inspired by a book written by Crispin Wright called Frege's Conception of Numbers as Objects. And that project attempts to resuscitate Frege's research program by trying to demonstrate that the truths of arithmetic can be deduced not maybe from principles of logic, but from principles of logic plus a principle that just kind of explains what numbers are. And indeed it does so in a way that Frege would really have liked. The principle that they use is the one that we actually talked about a few minutes ago. It's the principle that says this: the number of, and now I'm going to use the letters F and G in a way so that F might stand for people at the table and G might stand for chairs at the table, or F might stand for some other property and G for some other property. We want to know under what conditions are there just as many F's as there are G's. Well, as we talked about last time, the basic idea is there are just as many F's as there are G's if you can match up the F's one-to-one with the G's without any overlapping, without leaving anything out. Remember our example of the people and the chairs and the people sitting in the chairs. Okay, so here's the basic principle that neo-logicists use. They say you can explain what numbers are by saying this is the fundamental truth about numbers. The number of F's equals the number of G's if, and only if, there's a way of matching up the F's and the G's one-one with each other. And it turns out that principle is remarkably rich. If you use that principle, just that, plus some other principles of logic, you can get a lot of arithmetic. Indeed, you can get what we call the Peano axioms. And a lot of people think that's enough to show that something like logicism is true. Because that principle that I just gave you, even if you don't think of it as a truth of logic, it's not as obvious as the principle of if I have a red shirt and a black hat, then I have a red shirt. Nevertheless, it's something that you can know without going out and measuring anything or counting anything in the world. It looks like something you can know non-empirically. It looks like kind of just explaining what we mean by number of, or something like that. So the Neo-Logicist project is the project of trying to make the case, by giving lots of arguments and some interesting proofs, make the case that you can in fact, as it were, ground arithmetic in that principle plus logic. And the Neo-Logicists think that this tells us something very interesting about the nature of mathematical knowledge, that it really is something like what Frege thought it was. So that's an ongoing research project. Also, there's a lot of historical interest in the kinds of reductions that Frege managed to give just for mathematical reasons, not from the point of view of reducing mathematics to anything else. So that's another sort of historical legacy here.
So were mathematics and logic the only topics that Gottlob Frege wrote and thought about, or did he work in other areas of philosophy as well? How did this fit into his general philosophical picture?
Oh, another nice question. In fact, a lot of philosophy students know about Frege and they don't even know that he did philosophy of mathematics or logic, because a lot of his work has turned out to be very influential in a field that's called the philosophy of language. Philosophers of language are interested in questions about how it is that you and I use language to communicate. How is it that I get ideas from my head into your head just by making these kinds of sounds or writing marks on paper? And they're also interested in how our language gets to be about things in the world. So notice, for example, that you and I can talk now about the Eiffel Tower, even though it's not here. Somehow the words that I used got you to think about this object, and I managed to say something about this object that's very far away from us. So these are questions that many philosophers have thought of as very interesting, and they all come under the title of the philosophy of language. Frege was interested not so much in the language that we use to talk about things like the Eiffel Tower, though he did talk about that kind of language, but he was extremely interested in the languages that we use to do mathematics. So for the kinds of reasons that we've been talking about, he was interested in analyzing the meanings of various kinds of mathematical statements. And then he found that this was difficult to do without coming to a better understanding of what meaning really is. So you might ask yourself this: when you use a word, what exactly does the word mean? Like the word the Eiffel Tower. Okay, it's 3 words, but anyway, that phrase, the Eiffel Tower, does that mean the big tall thing over there in Paris, or does it mean the ideas that you and I have when we use the word, or like what exactly? And Frege had a number of things to say about that. The fundamental thing that Frege tends to be remembered for when it comes to language is that he thought that every piece of language has 2 different kinds of meaning. He called the first one the sense, and the second one the reference. So if you take a phrase like the Eiffel Tower, the reference of that phrase is that building, that tower there in Paris. It's an actual object. Whereas the sense is a rather more difficult to describe thing. It's what you and I grasp when we understand the word. So if someone is speaking to you in a language you don't understand, what you're not doing, thinks Frege, is associating the right sense with the words. So meaning in the sense of what you grasp when you understand the language, that's the sense of your words. And meaning in the sense of the stuff out there that you talk about, that's the reference of your words. And this holds even when your words aren't about physical objects like the Eiffel Tower. If you use the words, let's think of 2 phrases. Here's one, 2 + 2. And here's another one, 4. Those 2 phrases, interestingly, have what Frege thinks of as the same reference. They both refer to the number 4. But they do something that's quite different, because when I say 2 + 2 = 4, I say something quite interesting, well, at least a little bit interesting, more interesting than when I say 4 = 4. So the phrase 2 + 2, in some sense, has a different meaning than the word 4. And here's Frege's idea. The phrase 2 + 2 and the phrase 4 have different senses, though they have the same reference. And he thought that it was very important to explain how sense is related to reference, how sense is related to understanding, how reference is related to understanding, and things like this. And cashing out all of those ideas took quite a bit of work on his part. He wrote a number of essays that have become extremely influential in the philosophy of language, and a lot of work done today in the philosophy of language really can position itself. That is to say, people can explain where they stand on various issues by saying things like, well, I agree with Frege about this, but I disagree with Frege about that. His ways of thinking about language have had a lasting influence, even today, on the ways that we think about issues in the philosophy of language.
Patricia Blanchette, thanks very much for joining us.
You're welcome. Thanks, Matt. Thanks, Jamie. This was fun.
If you have any questions about this episode, you can post them to our blog at Lucian, that's lucian.uchicago.edu/blogs/elucidations. On the blog, you can get background information on the topics we covered and join in the discussion.